So in the previous section, we stop here, and then we went through the argument that this first correction terms, this one, is meant to be mixing in all the other zeroth order state with that not equal to n, okay? So therefore, I will write that expansion in now. The first order state, correction state, appear in two places. Yes, Wai Kin point out a very good point. Yes, I'm saving a notation. I should write it as AM, which is also depending on n. That is a matrix formally, okay? But I don't want the notation to be too scary. It's already scary for some students, I would say, okay? Get me? But good for you, you noticed that, okay? So let me get back here. I'm going to substitute in the expansion in the first term and in the last term, okay? So that's what I did in red. Psi n to the first order correction is now written as an expansion AM psi m0, the zeroth order state, but I'm skipping this particular one, okay? Meaning the correction is to mix in all the other to decorate the zeroth order one to approach the first order state. Similarly, the last term here, the expansion, okay? The first term here on the right-hand side disappeared due to orthogonality, okay? So now we can get the answer in two steps, rather interesting. Let's look at the very last one. Notice that this M will not hit, no. Okay, now this is I, anything other than N. So this one will be a delta function. It is not zero only when M hits I, okay? So it's a delta IM. Therefore, after I write it as delta IM, I can do the sum, okay? The sum will sooner or later hit I. Therefore, I will pick up AI times the zeroth order energy. Remember, when I'm left multiply into it by phi I0, the zeroth order state, I is not equal to n. So I is not n. This is exactly what we want to solve. Okay? We have another integral on the left-hand side. Again, it's easy. Once you do this expansion, this is an eigenstate of H0. So I pick up the eigenvalue, the nth one not equal to the n1, right? So EM0, the zeroth order thing, and the same integral, which is a delta function. Therefore, again, I can do the sum. Sooner or later, M will hit I pick up AI. Nonetheless, notice the difference. Here, when M hits I, this zeroth order energy becomes EI0, okay? Therefore, in one line, I move this term to the left-hand side, take AI out, I have a denominator, okay? Divide it through to the other side, we are done. The coefficients that we are looking for is very simple. Now, first of all, it's just a coefficient, a number. It should have no units. So look at the numerator. It is H prime in the middle, the perturbation, and telling us how much H prime can mix in some other state, the ith one, with N. Okay, now that makes sense because if H0 is not here, is 0, everything is 0. Meaning, if H prime is not there, the nth eigenstate, H0, and all the eigenstate of H0, they are orthogonal to each other. They have nothing to do with each other, okay? And H prime plays the role that can put some ith eigenstate to mix in to the nth state. And this is the strength, the power of H prime, okay? And this integral signifies how H prime is effective in doing that, okay? It is an energy, Hamiltonian is an energy, so this integration will give you some energy, all right? And the denominator is a difference in energy, okay? Now, pay attention. I'm asking for the nth state. This formula tells us there is another state I that can be lower than the nth state or higher than the nth state. There are many. This is the one you are asking for, okay? Some will be lower, some will be higher, okay? This denominator refers to the energy that you are asking, the state of the energy that you are asking, 0 for that, okay? Is it higher or is it lower than the state that is mixing in? This is the energy difference, okay? You may be asking how much this state affect you. You may be asking how much this state affect you, okay? This is the energy difference. Okay, do you follow me up to here? Is that okay? Yeah, okay. Now here's the punchline. Now follow me closely. H0 will have infinite many eigenstates, okay? With energy like this, okay? Now, you pick one called N and ask, how does H prime, the perturbation, will affect you? Okay? Now, first order in the state, it means the following. If you are asking about another state that will affect you that's very low in energy from your place, the effect will not be big, do you see? Because the energy difference appear in the denominator. Okay, do you understand what I'm saying? State with energy far away from you in H0 will not affect you much. They will have tiny, tiny, tiny effect on you. Okay, do you understand what I'm saying? This is just mathematics. You have to get some sense out of it, okay? Similarly, if you are asking for the effect of unperturbed state very high up in energy from where you are, and ask, hey, how will you affect me in terms of correction in this eigenstate? The simple answer is none, or approximately none, because the energy difference is very big. Okay, follow me? All right. Now that is to say, if you really worry about the first order correction in the state, you should worry about those unperturbed states with energy that are not too far away from you. Do you understand? The ones that will affect you most are the nearby ones in energy. Do you follow me? Okay. Now this is important quantum mechanics sense. All right. Okay. Now you have the ratio of two energies. Thereby, this expression is making sense. At least it is a coefficient. It's a number. Okay. And actually, after you realizing this meaning, you can again, without deriving it anymore, you can write down the expression. Okay. So let me go to the next page. Now I summarize two results. First order perturbation theory. We have derived formally the first order correction in energy, which is just what we guessed last time. And now we have a new result, the first correction to first order correction in the state. Okay. The thing in front is our coefficient AI. Do you see? Okay. H prime appears once. So now you understand this is the first order correction due to H prime to the state. If we don't stop here, we need to go back, look for the lambda square equation and look for psi and second order. In the answer, you will see two integrals with H prime in there. Okay, but we will not derive it for you here because in very rare situation, for problems in our course, we need it. Okay, so this is formally the first order perturbation theory result. All right. Now, I would like to make some very meaningful and physical discussion. As I said, a good theory will tell you when will it work or when will it not work for you. All right. Now here in particular, look at the first correction in the state. The whole thing we set up is meant to be small correction. This whole mixing in of the other state should be small correction to the zero for the state. However, if you look at the end result, you see a denominator, 分母啊，分母. If the denominator is not big, all right? In other words, if it is small, it may be problematic, right? What does it mean? This is a sum over all the other states except n, and it says, if there are some other zeroth order state, that is to say, this is the H0 problem. If you see in the H0 problem, when you ask for what happened to a state n, and there are some other state of this H0 problem that are very close in energy, then be careful. The answer tells you that, right? What will you call that situation? H0 situation when you have two states quite close to in energy. or three states very close in energy or equal to be extreme, you call that degenerate, right? You call it degenerate situation, right? Right? That is to say, the theory that we developed here should not work in case your chosen end state to ask the question has degenerate state in the known solvable problem. Okay, do you follow me? Now I would like to introduce the name of this theory. This theory is called time-independent non-degenerate perturbation theory, because you should not apply it when your state under consideration has degeneracy. Okay, do you understand? So now, okay, so this is where the title, the name comes in. All right, I don't like at the very beginning tell you this, okay? Too complicated, the name is, scare you off. Don't worry, at the beginning, work it out. In physics, when you're doing a project, try to take your calculation to completion, to the end. The end result will tell you something about the validity. That's most of the time like this, okay? So here is an example, all right? But I would also emphasize that don't wait for cases where you have EI0 really equal to EN0, real degenerate. You should be careful, even when you have some other state I that has energy already close to the one that you are considering. So not necessarily zero, that is the worst case, okay? But the nth one that you're asking, you see there are a lot, some states that are very close. Then it already is a warning sign. Be careful, okay? Don't overuse or abuse this non-degenerate perturbation theory, okay? Get me? Now, let's make more sense out of the result, okay? The derivation is simple, easy, I would say, but understanding the physics needs some time and effort, okay? So, I copy the result here again, and this is the first correction coefficient. As I already said, there are two parts, two ingredients, a numerator with H prime and an energy denominator, which is the difference. And that points at the validity, non-degenerate, use it comfortably. When there are states nearby, don't use it, try something else. And that something else is not complicated, it's rather easy, okay? We will develop a bit later, okay? And now, I have been saying when this is small, be careful, all right? Any physics students will challenge me. What do you meant by small? What is you meant by big? Okay. And now actually we have a comparison. The comparison is between the numerator and the denominator, right? It depends on how powerful H prime can connect other state to n. This integral, this matrix element formulae, h prime I n, that is an energy. And the energy difference between these two states. It is this ratio that really matters. Okay, and make good physical sense. We cannot just say very close, be careful. Maybe the numerator is 0. That's fine, right? Okay, so it is this comparison between the matrix elements up there and the energy difference down there that really matters. Okay, so this is the comparison. This thing is what we want to really quantify our validity. Okay, now nonetheless, if you really have very nearby energy, this is really an important warning sign. Okay, so schematically, now this is not good drawing, but it is the best I can do. Okay, now I hope that you understand what I'm trying to convey through this picture. Now this is the H0 problem. All these energies are known, and so are the states. All right. Now in perturbation theory, we've always start asking questions with choosing a particular state, okay, to do the job. We want the end state. We want to say, hey, what is the correction due to H prime? So this is the H problem, okay? How could this energy evolve to this hard to solve eigenstate for the nth state, okay? And we just found the new result for this correction to the state. What I'm saying is that the most important one will be yourself. That is the 0th order term. Okay, so you want the state, the 0th order term is yourself, 0th order. Okay, that may be 99% already. And now, if you want to include the more important thing, try those who have energies that are not too far away from you, nearby, okay? Because this will make the denominator not too big. This state inside this first circle will be the most important unperturbed state to mix in, to adjust your 0th order state to look like the perturbed problem eigenstate. Okay? Now, after that, if you are not satisfied, try to include a little bit more state farther in energy. Okay? Follow me? That is the dashed circle. But that is already less important. If you have a good computer, then you can include even more state that is farther away. But what you include in this bigger circle beyond the dashed line is really less important or not important at all. Okay? For the reason that the denominator become very big compared with this coefficient up there, this matrix element up there, so that this mixing in coefficient of those far away states to your focusing state will become negligible. Okay, so do you see the physical picture? Okay, so now, what about second order? You mean second order in the state or second order in the energy? Which one do you want? In the energy, okay. That will be our next task. Could you hold on? we will get a formula for it. Okay? And that, okay? I will tell you the answer immediately, actually. Let me see. The second order correction will be HIN squares, okay, due to the ith state divided by EN0 minus EI0. Okay, and then you sum over all I not equals to N. That is the second order correction in energy. Okay, so basically the criteria holds. Okay, we will see how this comes out. Not difficult at all. 3 more lines of mathematics. All right. So now at this point, let's take stock. We have the known problem X0. We make some effort and we get to the first order correction in energy and the first order correction in the state. The important thing about getting this first order to the state is that the results tell us the validity of the theory. Okay, that's pretty good. We know that now it is called non-degenerate perturbation theory. And another application of knowing the first order state is to get at the second order energy. All right, that we will do now. So the next task is to get at the second order correction in the energy. Okay, as Huang Haoxie point out. So this is the lambda square equation. All right, wow, looks complicated, right? But next, let's take stock. All the things with a tick above are known. X0, perturbation, no, right? If we don't know, we have nothing that we can do. And then we know the 0th order eigenstate, that is the unperturbed problem. We now know the first order energy after the first order derivation, okay? And we know the first order wave function. We know after the discussion just a while ago, okay? And we know this. So all the things with a tick are known, then the equation actually left us with 2 unknowns. The second order correction in energy, this is our task, and the second correction in the states, okay? So this is our enemy for the moment, EN2, okay? So what is the strategy? Make it stand out, right? Make it stand alone. Then we have an equation to solve for EN2. How to do it? I want to use normalization to get rid of this. So what to multiply in? Easy, right? Multiply in the 0th order n state, do integration. Okay? So let's do that. We have 5 terms. After we do this, intentionally, this becomes standalone. Okay? Now, let's look at, for example, this term. All right? Now, I'm multiplying the nth one, 0th one, but now the integration has to do with first order correction to this end state. Remember, this correction only makes in other states. It has no component of n. Therefore, every term will be 0 by orthogonal property. So this term is killed. Okay, nice. And then we have two terms remaining here and there we need to consider. Okay, now let's look at this term on the left-hand side. We multiply in an eigenstate of x0 by Hermitian condition. This can operate on this one, interchanging the two functions, and then that will pick up an eigenvalue. So I'm left with an integral like this. We don't know how to proceed because the second order correction in state is yet to be solved. That's why I leave it here. We cannot say it's zero, it's not zero, but we don't know. But we just leave it there. Okay, now let's look at this term. We multiply in n phi n0, do the integration. Again, we meet the same friend. And the prefactor is exactly what happened to the first term on the left-hand side. Thereby, despite we don't know what this integral is, they are identical on both sides, so cancellation works. Bravo! So we get an answer to the second order correction in energy, basically without effort. Okay? Nice. That is actually done, but I would say it's almost there because you do not see this result in this form in all the textbooks. But this is already the result, okay? I remember last time, someone asked me, what if I use the first order state? Okay, and then I say, hold on to the formal derivation. And this is the answer to that question, if you are still here today, all right? Okay, that is to say, if you invoke this, it happens to attach with an H prime as well, okay? Formal mathematics. But this is not the usual form expressed. The usual form makes use of the previous answer. Remember, we have expression for this first order correction in the state. So at this point, we would like to plug in the sum I, A, I, psi, I0 for the first order correction term. Okay, so that is the strategy. So we copy the result through. This is formally the answer, okay? But now we would like to further express it in a standard form. This thing, we know how to expand it. We found all the coefficients. First order result, thereby we substitute this in, okay? So we have sum over AI, this thing. Okay, remember, you are asking about nth correction, and this sum avoids the end state, non-degenerate theory. Okay, again, same thing. So now I explicitly plug in this coefficient. Okay, now you see the same old friend. This is a matrix element, n and I and n. Okay. That happens once, and if I substitute the coefficient in, it happens twice, okay? And very beautifully, I would say, now this is the matrix element H prime I n, I here, n here, and this is n I, okay? And we are dealing with Hermitian Hamiltonians. So this H prime is Hermitian, thereby they are related by a complex conjugate. So these two multiply together, you get a real number, don't worry. Now, matrix elements in general are complex. You are looking for correction to real energy. Thereby, at the end, you see this very comforting, right? At least we haven't made any mistakes. Well, we may be wrong in the other place, but at least the result in this form makes sense, okay? Now, this is one way to write down the result in shorthand notations, matrix element way, or if you want a full form in wave function ways, this is the second correction, okay? Again, it is very easy to remember. We already discussed this coefficient A that has to be dimensionless, no unit. But when we go to the energy, it has to be an energy. Thereby, it is good to see the square here. The matrix element itself is energy. Thereby, this is energy squared divided by the energy difference is an energy. Okay? So, again, there are physical sense. Okay? Now, look at this. The physical sense, again, let me stress, is more important than the derivation. You can always write down the equation on a piece of paper and then that's it. I will use it, okay? But you ought to understand the symbols and the physical content in the equations. Here, let me explain a little bit. Again, we have a numerator and a denominator, okay? And in this situation, we are talking about the second order correction in energy, okay? So, as in the past, the matrix elements reflects how strong another state I can affect you through H prime, okay? Nothing new, but now it depends on this thing, absolute square. So that is a real thing, energy square term, okay? Now, the more important thing is now the denominator. Nothing new, again. If a state is below you far, far away, the effect will be small. If a state is above you far, far away, the effect is small. Nothing new, same situation. But there's a new element. Pay attention. This is the energy, right? And now, unlike the wave function, plus sign and minus sign has physical meaning. So look at these terms. It is summing over all other states I. So this is my n. If I'm considering state I that are lower in energy than me in the unperturbed problem, okay? Now, physically it means in the second order correction, this lower state will try to push my energy up. Now, this is a punchline statement. So do you understand what I'm saying? Because En is higher than Ei0. Okay, it's positive. The numerator is positive always, right? So all the lower the state lower than you in H0 will tend to push your energy up. All the state above you in H0 will tend to push you down. The end result is the net effect of all this pushing. Do you understand what I'm saying? Okay? Very layman language, but we are discussing something very profound in physics. Okay? So the second order equation can be taken as very lively. Okay, this thing are trying to push me up, this thing are trying to push me down, and more. The states that are near to energy, to me, they have a bigger power to push me up. The states that are nearby but above me in energy has a bigger power to push me down. Those stay far away, they are pushing, right, but negligible effect. Okay, understand? Understand? Okay, understand? Tanda? Now, some of you may need some immediate application. Okay, now, for example, we are discussing a molecule problem. I have a hydrogen fluoride, okay, HF. So I can immediately, if you go to chemists, they will say, okay, now, hydrogen has a 1s state. Fluorine, there is a 2p electron waiting to form bond. Okay? Then you look up atomic energy. Hydrogen 1s is up here. Fluorine 2p is somewhere here. Okay? And then the two atoms comes together. You only have two states. You're sitting on the hydrogen, you ask, hey, what does this do to me? It's pushing me slightly higher. And then you sit on the fluorine, hey, what does the hydrogen 1s do to me? It's pushing me lower because it is above me. Okay? So at the end, you will see things like okay, hydrogen 1s, fluorine 2p, and then one is pushed up, one is pushed down. Okay, those of you who have taken 1070 or other chemistry course should have seen such diagram, I think. Okay, and then there's a 1s electron, there is a 2p electron, thereby they go in here, and then you say, okay, HF form this bond. Okay, and this, behind this thing, the mathematics is exactly what I just described to you, or the physical picture is exactly what I described to you. Okay, H prime in this case is when the two atoms comes together, okay, the electron here started to see another nuclei. The electron here started to see another nuclei. Is different from what it sees in an atom alone. That is H prime. Okay, so with that, I will stop here today. Okay, I will stay around to see if you have questions. Bye-bye.